Electromagnetic induction is probably one of the most important bits of this course, which I'll be teaching. Electromagnetic induction and its application in the world of electronics in the form of transformers. No, they're not in disguise. They're not those giant robots that you see on TV. These are electrical transformers. So I think we reviewed in a previous lesson what electromagnetic induction is. I think we perhaps looked at what a solenoid is and reviewed the fact that a solenoid carrying a current generates a magnetic field. So in this case, let's say we have a solenoid and current flows in this direction. What you can do to work out the direction of the bar magnet that's formed is by wrapping your fingers around the direction of the current. That way your thumb will be pointing in the direction of the North Pole. So this will be the North Pole, this will be the South Pole. And very similar to a bar magnet, you have lines passing through. Very similar to a bar magnet. Okay? And that's something that you have to understand. Now, similar to this notion, this magnetic field that's induced in this coil, if we connect this up to another coil, per se, let's say it's this coil. Okay, this coil is going to come in, it's going to be another coil. Let's say it has more turns. Okay, this coil has more turns, and it's not got a current, but it's attached to a galvanometer. Okay, galvanometer, very similar to a voltage meter, a voltmeter. Now, per se, if we connect this coil up, or at least bring them into close proximity, what you'll find is these lines of flux, these force lines, magnetic force lines, will tend to pass through this coil, cutting it at an angle of 90 degrees. Now, this is something that you really must understand. When you cut a coil by 90 degrees with magnetic lines of flux, what you generate is an EMF. An EMF is generated. Now, you probably have come across this equation already. I probably reviewed it in a previous lesson, but you might not have understood it. So we'll review it again. This equation is a combination of Faraday's law and Lenz's law. Now, what Faraday's law states is that there will be an electromagnetic force, an electromotive force, an EMF will be generated where there is a rate of change of flux linkage. Okay, this is the rate of change of flux linkage. Now, flux linkage is very similar to what it sounds. It's basically the linking of the flux from the primary coil. In this case, this coil that's generating the flux, the coil that has the current passing through it, is generating flux that links. It links with the secondary coil. Okay? And this flux linkage depends on two factors. It depends on the flux from the primary, so this is based on the primary coil, and the number of turns on the secondary coil. Okay? The number of turns on the secondary coil. And the rate of change of this is determined when there's a change in the current that's being generated here. So, for example, if this were an AC current, okay? If this was an AC current, what you'd have is this changing from north to south and south to north, alternating. And the flux lines that are passing through this coil will be alternating from down to up to down to up. And because of the fact that they're cutting the coil, the secondary coil, perpendicularly, what you'll have is this figure over here, this rate of change of flux linkage that's occurring. And this rate of change of flux linkage will generate an EMF which can be measured by this galvanometer over here. Now, theory states that ideally, an ideal transformer will obey an equation. And this equation I'm going to write down here. Okay, so what we have here is the EMF of the primary circuit over the number of turns on the primary coil is equal to the EMF of the secondary circuit divided by the number of coils on the primary circuit. Now, it's very simple to derive this. I can actually do it right now, probably. If we forget about the minus sign for now, what you can find from this equation that we have above here is that E over N is equal to d phi over dt. Now d phi over dt is the same for both coils. So assuming that the flux that's passing from this coil to the secondary coil is instantaneous, so the rate of change will be an instant event. So we're assuming that it's an instant event, and it's also constant for both the coils. The flux that's passing through both coils should be constant. Assuming that fact, if this is a constant, then we know that the EMF in the primary coil and the EMF in the EMF in the secondary coil and the number of turns in the secondary coil should be equal as a result, and therefore we have this equation that we have seen over here. And this is an equation that you have to understand, but there's a problem. This equation is only for ideal transformers. So this is a transformer which obeys all these assumptions that we've made. It's an ideal transformer. In reality, of course, transformers don't obey all those assumptions that we've made. An ideal in reality, we can talk about what these shortcomings are. In reality, however, firstly, not all flux from the primary coil goes to the secondary coil. If we look at this this diagram, very crude diagram here, you'll have some flux lines that are passing off to the left that aren't really being connected to this secondary coil. And that is a problem, because then our equation that we've worked out here will not be accurate as a result. Not only that, you also have some other problems. You have resistance in the wires. Now, from a previous lesson, you should know that the flux is determined by this equation. So the flux that's generated by a solenoid is determined by an equation that is basically somewhat like this. So in the case of the primary solenoid, N stays constant and phi stays constant. Or sorry, not phi, sorry, this, I don't know what this is called. It's the permeance basically, and in this case it's air. That stays constant. This factor, however, the current will be decreased if we have increased resistance in the circuit due to resistance in the wire. And as a result, you'll have decreased phi being produced, or decreased flux. So there'll be fewer flux lines that are passing to the secondary coil. And if there are fewer flux lines passing to the secondary coil, then the EMF that's generated in the secondary coil will be lower than what's predicted by this equation. So that's another problem that we have to overcome. Now, these are the two main problems. The way we can overcome not all the flux passing from the first to the second is by using this thing called a permeant core. So I'm gonna actually delete everything off this board. So okay, I have more space to work with. A permeant core is basically an iron core. Now, iron is permeant because iron is a ferromagnetic material. Okay, and it basically allows the completion of a magnetic circuit. So let me quickly draw. This is an iron core. Okay, and you'll have your primary coil over here. We'll coil around this end of the core, and you'll have your secondary coil over here. So wrap around this end of the core. Of course, let's say your secondary end has more turns. Right. Now, in this case, what you can probably see now is the fact that these flux lines that before that tended to go off to the left, they'll actually be restricted to this magnetic circuit that's provided by the iron core. Because one of the factors that you must understand about magnetic circuits is magnetic circuits always favor the path of least resistance, and hence like to shorten themselves as much as possible. If we're providing a permeant core in the form of this iron core, it's much more permeant than the air, the surrounding air, and as a result the flux lines will tend to be contained within this structure, which is very important because now most of the flux lines are passing from the primary core to the secondary core, and it helps us justify using this ideal transformer equation to work out what the different voltages will be, how the voltage will be stepped up or stepped down based on the number of turns on each coil. So of course that's one way of overcoming it. Now of course the second thing I mentioned was in terms of the resistance of the wires, but we have to consider something else. Going back to this equation which I mentioned just a few seconds ago, this factor over here, which is known as the permeance, this is proportional to, or at least is equal to, permeability of a substance, which is constant, and it's very high for iron, and it's proportional to these factors. So we need to make an iron core fat, or a coil fatter, increase the thickness of it, and we also need to make it short and fat. In essence, what we want to do then is increase the thickness of this core, so make this core thicker, i.e. make the coil thicker, and also we want to decrease this distance over here downwards, because what that will allow is for a shorter circuit to form, a shorter magnetic circuit, and the shorter the magnetic circuit, the more the flux can be generated, and the more effective flux that's passing from the primary core to the secondary core, and that's much more favorable. Okay? However, having said that, if we want to maximize the current's resistance, or resistivity, is measured in, well, wait a minute, I forgot what the values are. Let me just write it down. Resistivity is proportional to a constant. I'm not sure what the constant, I forgot the equation, but it's proportional to the very same things. Oh, sorry, not resistivity. It's not proportional, it's proportional to this. So resistance increases as your length increases. Oh my god, I'm sorry, one second. Not resistivity, conductivity. Yeah, here we go. Conductivity is proportional to the same thing. So you'll have a conductance of the wire increased as you increase the area. So the thickness of the wire, as you increase it, it will have more conductance, and it will reduce the resistance. And also you want to reduce the length of the wire that you're using. However, if you decrease the length of the wire that you're using, what's going to happen to the number of coils that you have? It's going to be less if you're using less wire, right? As a result, you guys can see all the different factors that are at play when you're trying to create an ideal transformer, and it's very difficult to. However, in an exam situation where they ask you to try and improve a circuit, you have to look for factors like the permeance that's involved. Is there any air gaps in your magnetic circuit? Could you add a core perhaps? Could you increase the number of turns on one of the coils if you want to generate a larger EMF in the secondary coil? Increase the number of turns. Could you perhaps decrease the resistance in the coils by making some adjustments? Could you, I don't know, increase the area of the coil or the core and decrease the length of the core? All these different factors you can quote in order to improve a magnetic circuit. But of course, a compromise has to be reached with transformers and the likes as such. This video is getting really long, so I'm going to cut it short here for now, and I hope to see you guys in the next video where we'll be discussing something very similar. Catch you later. Bye bye.